Okay. So in the previous example, we went through this process of pick a starting number, form or sketch the tangent line at this location xn by forming the corresponding tangent line. Find where this tangent line has an intercept. In other words, where does it cross the x-axis? Set the value of the intercept of this line as our next x value, n plus 1. Repeat. So that's the basic algorithm. Now, using a formula, how do we get what x sub n plus 1 is if we know what x sub n is? Well, it turns out it's this. This is the process. Well, let's go ahead and prove this. We'll derive this formula. It's very simple. So let's quickly just draw a graph here to give us something to work with. So here's a graph. And let's say we've got some function f. And at some value here, let's say right here, we'll call this xn. At that point, we form the tangent line. So that's our ln. And now this is going to cross eventually. Crosses someplace. This intercept right here is our x sub n plus 1. So how are we going to get this? Well, let's go ahead and form the linearization. So L sub n of x, the linearization, this is f of xn plus f prime of xn times x minus xn. Now we want to know when this equals 0, because that's how you find when a function crosses the x-axis. So then if we begin and solve for this x value to see where it crosses, we will have negative f of xn over f prime of xn. And here you can also see why we can't have horizontal tangent lines. Because if the linearization to f at xn is a horizontal line, that means f prime of xn is 0, and then we'd be dividing by 0. So that's also bad. This is equal to x minus xn. If we solve for the x-intercept, this is xn minus f of x sub n all over f prime of x sub n. This gives us the next value, so this right here we just decide to rename as x sub n plus 1. And then that proves, or at least derives, that expression.